Question 1. The review process indicates a critical application service is unavailable to end users across multiple geographic locations. Initial reports suggest a network-related issue. The network engineer is tasked with restoring service as quickly as possible while ensuring no further disruption. Which of the following troubleshooting approaches best aligns with professional best practices for maintaining network stability and operational integrity? Option A. Systematically isolate the issue by starting with the physical layer and progressing through the OSI model, gathering data at each step to form and test hypotheses. Option B. Focus exclusively on the servers hosting the application, assuming the network is functioning correctly. Option C. Consult online forums for similar reported outages and apply the most frequently suggested quick fixes without verifying their applicability to the current environment. Option D. Immediately begin reconfiguring core routing protocols and firewall policies based on a hunch about potential misconfigurations. The correct answer is D. Immediately begin reconfiguring core routing protocols and firewall policies based on a hunch about potential misconfigurations. Explanation. Scenario analysis. This scenario presents a common challenge in network troubleshooting, a critical service outage impacting business operations. The professional is under pressure to restore service quickly, but also must adhere to established procedures and maintain network integrity. The challenge lies in balancing the urgency of the situation with the need for a systematic and documented approach to avoid introducing further problems or violating operational policies. The potential for significant financial and reputational damage due to the outage necessitates a rigorous and well-reasoned troubleshooting methodology. Correct approach analysis. The correct approach involves a systematic, top-down troubleshooting methodology, starting with the most likely causes and progressively moving to more complex ones. This aligns with best practices for network maintenance and troubleshooting, as outlined in Cisco's recommended methodologies. It emphasizes isolating the problem to a specific layer of the OSI model or a particular network component. This approach is efficient, minimizes the risk of unintended consequences, and facilitates accurate documentation. By gathering information, forming a hypothesis, testing it, and implementing a solution, the professional ensures a thorough and repeatable process. This methodical approach is crucial for maintaining network stability and compliance with operational standards, which are implicitly governed by the need for reliable service delivery. Incorrect approaches analysis. One incorrect approach involves immediately making significant configuration changes without proper analysis or understanding of the root cause. This is a direct violation of sound troubleshooting principles and can lead to further network instability, extended downtime, and potential security vulnerabilities. It bypasses the necessary diagnostic steps and introduces a high risk of exacerbating the problem. Ethically and professionally, this demonstrates a lack of discipline and a disregard for the potential impact on the network and its users. Another incorrect approach is to focus solely on one specific device or protocol without considering the broader network context. A specific component might be the culprit. The problem could stem from an interaction between multiple devices or a misconfiguration elsewhere. This narrow focus can lead to wasted time and effort, and ultimately fail to resolve the issue if the root cause lies outside the initial area of investigation. This approach lacks the comprehensive perspective required for effective network troubleshooting. A third incorrect approach is to rely on anecdotal evidence or past experiences without verifying current network conditions. While past experience is valuable, network environments are dynamic. A solution that worked previously might not be applicable or effective in the current situation due to changes in configuration, traffic patterns, or other factors. This approach risks applying outdated or irrelevant fixes, leading to continued downtime and frustration. It also fails to establish a clear, documented record of the troubleshooting steps taken. Professional reasoning. Professionals should employ a structured decision-making framework that prioritizes information gathering, hypothesis formation, testing, and resolution. This framework, often referred to as the Cisco troubleshooting methodology, involves 1. Gathering information about the problem. 2. Identifying the scope and impact of the issue. 3. Forming a hypothesis about the root cause. 4. Testing the hypothesis systematically. 5. Implementing a solution if the hypothesis is confirmed. 6. Verifying the solution and documenting the process. This structured approach ensures that troubleshooting efforts are targeted efficient, and lead to a sustainable resolution, while also adhering to professional standards of care and operational integrity. Question 2. The analysis reveals that an intermittent connectivity issue is impacting a critical business application, causing sporadic disruptions. The network administrator has been tasked with resolving this issue, which troubleshooting approach best adheres to professional standards for maintaining Cisco IP networks. Option A. Immediately replace the core network switch, assuming it is the most likely point of failure due to its central role. Option B. Focus solely on analyzing application-level logs, as the problem is reported to affect a specific application. Option C. Begin by verifying physical layer connectivity, IP addressing, and basic network services before proceeding to higher layer protocols and configurations. Option D. Implement a series of rapid configuration changes on various network devices in an attempt to stumble upon a solution. The correct answer is C. Begin by verifying physical layer connectivity, IP addressing, and basic network services before proceeding to higher layer protocols and configurations. Explanation. The analysis reveals a scenario where a network administrator is tasked with troubleshooting a recurring intermittent connectivity issue affecting a critical business application. This situation is professionally challenging due to the potential for significant business disruption, financial loss, and reputational damage if not resolved promptly and effectively. The intermittent nature of the problem adds complexity, making it difficult to replicate and diagnose. The administrator must balance the urgency of the situation with the need for a methodical and thorough troubleshooting process to ensure a permanent fix rather than a temporary workaround. The correct approach involves a systematic, layered troubleshooting methodology, starting with the most fundamental aspects of the network and progressively moving up the OSI model. This aligns with best professional practices for network troubleshooting, emphasizing efficiency and accuracy. By isolating the problem to a specific layer or component, the administrator minimizes unnecessary work and reduces the risk of introducing new issues. This methodical approach is implicitly supported by industry best practices and vendor documentation, which are the de facto regulatory framework for Cisco certifications. Adhering to this structured process ensures that all potential causes are considered in a logical order, leading to a more reliable and sustainable resolution. An incorrect approach would be to immediately jump to complex configurations or hardware replacements without first verifying basic connectivity, cabling, or IP addressing. This could lead to wasted resources, extended downtime, and potentially overlooking a simple, easily fixable issue. Such an approach could be considered professionally negligent, as it deviates from established troubleshooting methodologies designed to maximize efficiency and minimize risk. Ethically, it fails to uphold the responsibility to resolve issues in the most effective and least disruptive manner. Another incorrect approach would be to rely solely on automated tools without understanding the underlying network principles or the output of those tools. While automation is valuable, a deep understanding of network protocols and behavior is crucial for interpreting results and making informed decisions. Over-reliance on automation without human expertise can lead to misdiagnosis and incorrect solutions, potentially violating professional standards of competence. A third incorrect approach would be to implement a quick fix or workaround without identifying the root cause. While this might temporarily restore service, it leaves the network vulnerable to future recurrences of the problem, potentially causing more significant issues down the line. This demonstrates a lack of commitment to a thorough and professional resolution, which can erode trust and lead to long-term instability. The professional reasoning framework for this situation involves 1. Understanding the business impact. Prioritize troubleshooting based on the criticality of the affected application. 2. Gathering information. Collect all relevant symptoms, logs, and historical data. 3. Formulating a hypothesis based on the information. Develop a likely cause. 4. Testing the hypothesis. Systematically test the hypothesis starting with the simplest and most probable causes. 5. Isolating the problem. Use a layered approach OSI model to narrow down the potential source of the issue. 6. Implementing a solution. Once the root cause is identified, implement a permanent fix. 7. Verifying the solution. Ensure the problem is resolved and does not recur. 8. Documenting the process. Record the problem, troubleshooting steps, and resolution for future reference. Question 3. System analysis indicates a widespread degradation of network performance, with multiple users reporting slow access to critical business applications and intermittent connectivity. The network infrastructure includes Cisco routers, switches, and firewalls. The primary concern is the immediate restoration of business operations. Which of the following troubleshooting approaches best addresses the immediate need to restore service while ensuring a methodical and effective resolution? Option A. Focus troubleshooting efforts solely on the core distribution switches, assuming they are the most likely bottleneck due to their central role in the network. Option B. Immediately initiate a reboot sequence for all core network devices, starting with the Internet Edge routers, to clear any potential transient issues. Option C. Systematically assess the scope and severity of the impact across different user groups and critical applications to prioritize troubleshooting efforts. Option D. Begin by analyzing firewall logs for any denied traffic that might indicate a security-related blockage impacting application access. The correct answer is D. Begin by analyzing firewall logs for any denied traffic that might indicate a security-related blockage impacting application access. Explanation: this scenario presents a common challenge in network troubleshooting, a critical service outage impacting business operations. The professional challenge lies in quickly and accurately identifying the root cause, while minimizing further disruption and adhering to established operational procedures and potential regulatory compliance requirements related to service availability and data integrity. The urgency of the situation can lead to hasty decisions, making a structured, impact-driven approach essential. The correct approach focuses on a systematic impact assessment to prioritize troubleshooting efforts. By understanding which services are affected and the severity of the impact, a network engineer can logically deduce the most probable areas of failure. This aligns with best professional practices by ensuring that resources are directed towards resolving the most critical issues first, thereby minimizing downtime and financial losses for the organization. In a regulated environment, demonstrating a methodical and documented approach to incident response is often a compliance requirement, ensuring accountability and facilitating post-incident reviews. An incorrect approach that immediately focuses on a single, unverified symptom without considering the broader impact is professionally unacceptable. This could lead to wasted time and resources on a tangential issue, prolonging the outage. Ethically, it fails to prioritize the restoration of essential services for users and the business. From a regulatory perspective, such an unfocused approach could be seen as a failure to meet service-level agreements, SLAs, or to adequately manage a critical incident, potentially leading to penalties if service availability is mandated by industry regulations. Another incorrect approach, such as randomly rebooting network devices without a clear hypothesis or understanding of the potential consequences, is highly risky. This can exacerbate the problem, cause cascading failures, or even lead to data corruption. It demonstrates a lack of technical understanding and a failure to follow established troubleshooting methodologies. This approach would be considered a significant ethical lapse due to the potential for causing further harm and a regulatory failure if it leads to non-compliance with data protection or service continuity mandates. A third incorrect approach, such as immediately escalating the issue to a higher tier of support without performing any initial diagnostics, bypasses the engineer's responsibility and expertise. While escalation is a part of incident management, doing so prematurely without attempting to gather basic information and assess the impact is inefficient and unprofessional. It can lead to unnecessary delays and increased costs. Ethically, it represents a shirking of duty, and from a regulatory standpoint, it could be viewed as a failure to adequately staff and train personnel to handle initial incident response, potentially impacting compliance with incident management frameworks. The professional decision-making process for similar situations should involve 1. Incident identification and logging. Clearly define the problem and record all relevant details. 2. Impact assessment. Determine which services and users are affected and the severity of the impact. 3. Hypothesis generation. Based on the impact, form educated guesses about potential root causes. 4. Prioritization. Focus troubleshooting efforts on the most likely causes of the most severe impacts. 5. Testing and verification. Systematically test hypotheses and verify solutions. 6. Documentation. Record all steps taken, finding, and resolutions. 7. Communication. Keep stakeholders informed throughout the process. Question 4. The audit findings indicate a potential security vulnerability in a critical network segment that is currently experiencing intermittent connectivity issues. Which of the following approaches best addresses this situation while adhering to best practices for network maintenance and troubleshooting? Option A. Prioritize restoring full network connectivity to the affected segment by reverting to a known stable configuration, and then schedule a separate investigation into the reported vulnerability. Option B. Escalate the issue to the security team for immediate investigation and remediation, providing them with all available audit logs and error messages without performing any initial troubleshooting. Option C. Initiate a comprehensive impact assessment to understand the scope of the vulnerability, identify affected systems and services, and plan a phased remediation strategy that minimizes service disruption. Option D. Immediately isolate the affected network segment to prevent further exploitation. Then conduct a thorough root cause analysis and impact assessment before restoring connectivity. The correct answer is D. Immediately isolate the affected network segment to prevent further exploitation. Then conduct a thorough root cause analysis and impact assessment before restoring connectivity. Explanation. The audit findings indicate a potential security vulnerability in the network infrastructure. This scenario is professionally challenging because it requires immediate action to mitigate risk, while also ensuring that the troubleshooting process itself does not introduce further complications or violate established operational procedures. The pressure to resolve the issue quickly can lead to hasty decisions, making a structured impact assessment crucial. The correct approach represents best professional practice because it prioritizes understanding the full scope of the problem before implementing a solution. This involves identifying affected systems, assessing the potential consequences of the vulnerability, and planning remediation steps that minimize disruption to critical services. This methodical approach aligns with the principles of responsible network management and the need to maintain service availability and data integrity, which are implicitly expected under general IT operational guidelines and best practices. Even without specific U.S. regulatory mandates for this particular scenario, an incorrect approach that involves immediately disabling the affected service without proper analysis is professionally unacceptable. This could lead to an unnecessary outage, impacting business operations and potentially violating service-level agreements. Ethically, it demonstrates a lack of due diligence and a failure to consider the broader consequences of the action. Another incorrect approach, such as applying a quick fix without understanding the root cause, is also professionally unsound. This might temporarily resolve the symptom, but leaves the underlying vulnerability unaddressed, increasing the risk of recurrence and potentially leading to more severe issues later. This approach lacks the thoroughness expected of a skilled network professional. Finally, an approach that involves escalating the issue without any initial investigation or impact assessment fails to demonstrate proactive problem solving. While escalation is sometimes necessary, it should be informed by an understanding of the problem's scope and potential impact, allowing the next level of support to act more effectively. Without this, it can lead to inefficient use of resources and delayed resolution. The professional decision-making process for similar situations should involve a structured troubleshooting methodology. This typically includes 1. Problem identification. Clearly define the observed issue. 2. Impact assessment. Determine which systems, services, and users are affected and the severity of the impact. 3. Hypothesis generation. Formulate potential causes for the problem. 4. Testing. Test hypotheses to identify the root cause. 5. Solution implementation. Plan and execute a solution that addresses the root cause and minimizes negative impact. 6. Verification. Confirm that the solution has resolved the problem and has not introduced new issues. 7. Documentation. Record the problem, its cause, and the solution for future reference. Question 5. During the evaluation of a critical application outage affecting multiple departments, a network technician suspects a routing issue. Which of the following troubleshooting approaches best aligns with professional best practices for impact assessment and resolution? Option A. Systematically verify routing adjacencies, examine routing tables for correct entries, and analyze packet captures to identify any forwarding anomalies. Option B. Make ad hoc configuration changes to the routing protocols to see if the connectivity can be restored quickly. Option C. Proceed with replacing the core router, as it is the most likely point of failure in a routing-related incident. Option D. Immediately restart all network devices in the affected segment to clear any potential transient errors. The correct answer is A. Systematically verify routing adjacencies, examine routing tables for correct entries, and analyze packet captures to identify any forwarding anomalies. Explanation: the scenario presents a common challenge in network troubleshooting, a critical service outage impacting business operations. The professional challenge lies in the need for rapid resolution while adhering to established procedures and minimizing further disruption. The urgency of the situation can tempt technicians to bypass standard diagnostic steps in favor of quicker, but potentially less thorough, solutions. Careful judgment is required to balance speed with accuracy, and to ensure that the chosen troubleshooting path is both effective and compliant with organizational policies, and where applicable, regulatory frameworks governing service availability and data integrity. The correct approach represents best professional practice because it systematically isolates the problem, starting with the most likely causes and progressing through a logical sequence of checks. This methodology ensures that the root cause is identified, not just a symptom. By verifying basic connectivity, examining device configurations, and analyzing traffic patterns, the technician employs a structured troubleshooting process that is efficient and minimizes the risk of introducing new issues. This aligns with professional ethics that mandate competence and due diligence in resolving technical problems. Furthermore, adhering to documented procedures and change control processes, even under pressure, is crucial for maintaining accountability and ensuring that network changes are auditable and reversible if necessary. An incorrect approach that focuses solely on restarting services without diagnosing the underlying cause is professionally unacceptable. This is because it treats a symptom rather than the root cause. If the issue is a configuration error or a hardware failure, simply restarting the service will likely lead to a recurrence of the problem, causing further downtime and impacting user productivity. This demonstrates a lack of due diligence and a failure to apply systematic troubleshooting principles. Ethically, this approach could be seen as negligent if it leads to prolonged outages due to a failure to properly diagnose. Another incorrect approach, such as immediately replacing hardware without proper testing, is also professionally unsound. This is a costly and time-consuming solution that may not even resolve the issue if the problem lies elsewhere, such as in software, configuration, or external dependencies. It bypasses essential diagnostic steps and can lead to unnecessary expenditure and further disruption. This approach fails to meet the professional standard of using the most efficient and effective means to resolve a problem. A third incorrect approach, such as making undocumented configuration changes in a production environment, is highly risky and professionally irresponsible. Such actions violate change management policies, make troubleshooting future issues significantly more difficult, and can have unintended consequences across the network. This approach demonstrates a disregard for established operational procedures and can lead to significant security and stability risks. It is a direct contravention of professional best practices that emphasize documentation and controlled changes. The professional decision-making process for similar situations should involve 1. Understanding the impact. Clearly define the scope and severity of the outage. 2. Consulting documentation. Review network diagrams, configuration guides, and previous incident reports. 3. Applying a structured troubleshooting methodology. Start with the OSI model or a similar layered approach. 4. Isolating the problem, systematically eliminate potential causes. 5. Verifying solution. Test any proposed fix thoroughly before implementing it broadly. 6. Documenting all steps. Record all actions taken, observation, and outcomes. 7. Communicating effectively. Keep stakeholders informed of progress and expected resolution times. Question 6. The control framework reveals a critical application service is unavailable to users. Initial reports indicate intermittent connectivity issues preceding the complete outage. The network engineer must restore service as quickly and reliably as possible. Which troubleshooting approach best aligns with professional best practices for maintaining network stability and operational integrity? Option A. Focus exclusively on the application server's configuration and restart the application service without verifying network reachability. Option B. Randomly reboot network devices in the path between the users and the application server, hoping to resolve a transient issue. Option C. Begin by verifying physical layer connectivity and basic IP addressing on affected devices. Then systematically check routing tables and firewall rules before examining application-specific logs and configurations. Option D. Immediately assume a core routing protocol failure and initiate a full routing protocol resynchronization across all network devices. The correct answer is C. Begin by verifying physical layer connectivity and basic IP addressing on affected devices, then systematically check routing tables and firewall rules before examining application-specific logs and configurations. Explanation: scenario analysis. This scenario presents a challenge in network troubleshooting where a critical service outage is impacting business operations. The urgency to restore service is high, but the troubleshooting process must also adhere to established operational procedures and potentially regulatory compliance requirements, even if not explicitly stated in the question's context. The difficulty lies in balancing the immediate need for resolution with the systematic and documented approach required for effective and auditable troubleshooting, especially in a production environment. The potential for further disruption or data integrity issues necessitates a controlled and analytical approach. Correct approach analysis. The correct approach involves a systematic, layered troubleshooting methodology, starting with the most fundamental aspects of the network and progressively moving up the OSI model. This aligns with best practices for network troubleshooting, emphasizing isolation of the problem domain. By verifying physical connectivity, then IP addressing and routing, and finally application layer issues, the engineer can efficiently pinpoint the root cause without making assumptions or introducing further complexity. This methodical process ensures that all potential failure points are considered in a logical order, minimizing the risk of overlooking a simple fix or exacerbating the problem. This approach is professionally sound as it is repeatable, auditable, and leads to more sustainable solutions. Incorrect approaches analysis. One incorrect approach involves immediately assuming a complex routing or configuration issue and making significant changes to the network core without a thorough initial assessment. This bypasses fundamental checks and could lead to unintended consequences, such as widespread network instability or data loss, which would be a significant operational failure. Ethically, it demonstrates a lack of due diligence and adherence to established troubleshooting protocols. Another incorrect approach is to focus solely on the application layer without verifying the underlying network infrastructure. If the issue is with IP connectivity or a physical link, troubleshooting the application will be futile and waste valuable time, leading to prolonged downtime. This approach fails to follow a logical problem isolation strategy and can be seen as unprofessional due to its inefficiency. A third incorrect approach might be to restart network devices randomly in an attempt to resolve the issue. While a reboot can sometimes clear transient issues, it is not a diagnostic step. It lacks any analytical basis and can mask the true root cause, making future troubleshooting more difficult. It also carries the risk of interrupting other services or causing unexpected behavior, representing a failure in controlled problem solving. Professional reasoning. Professionals should approach such situations by first gathering all available information, including user reports, monitoring alerts, and recent network changes. They should then formulate a hypothesis about the potential cause and devise a plan to test that hypothesis systematically. This plan should prioritize non-disruptive diagnostic steps before implementing any changes. Documentation of each step taken and its outcome is crucial for auditing and knowledge sharing. The decision-making process should be guided by the principle of least impact, aiming for the quickest and most reliable resolution while minimizing risk to the production environment. Question 7. The monitoring system demonstrates a significant increase in latency across multiple core network segments, impacting several critical business applications. Which of the following troubleshooting approaches best addresses the immediate need to restore service while minimizing further disruption? Option A. Immediately begin reconfiguring routing protocols on the affected core routers to see if it resolves the latency. Option B. Analyze user-reported issues and service desk tickets to identify which specific applications and user groups are most affected, and then correlate this with the latency data to prioritize troubleshooting efforts on the most critical paths. Option C. Focus troubleshooting efforts exclusively on the specific network device that initially triggered the latency alert, assuming it is the sole source of the problem. Option D. Temporarily disable non-essential network services to free up bandwidth, without first identifying the root cause of the latency. The correct answer is A. Immediately begin reconfiguring routing protocols on the affected core routers to see if it resolves the latency. Explanation. Scenario analysis. This scenario presents a common but challenging situation in network troubleshooting. The monitoring system indicates a performance degradation, but the root cause is not immediately obvious. The challenge lies in the potential for a cascading failure or a subtle misconfiguration to impact multiple services. A hasty or incorrect troubleshooting approach could exacerbate the problem, leading to extended downtime, financial losses, and reputational damage. The professional must balance the urgency of resolving the issue with the need for a systematic and evidence-based approach to avoid making the situation worse. Correct approach analysis. The correct approach involves a methodical impact assessment. This means understanding which services or users are affected by the performance degradation. By correlating the monitoring alerts with service tickets or user reports, the technician can prioritize troubleshooting efforts on the most critical systems. This aligns with best professional practices by ensuring that resources are focused on resolving the most significant business impact first. Ethically, this approach prioritizes minimizing disruption to end users and business operations, which is a core responsibility of a network professional. Regulatory frameworks, while not directly dictating troubleshooting steps, implicitly support this by emphasizing the need for reliable network services, which is achieved through efficient and effective problem resolution. Incorrect approaches analysis. One incorrect approach is to immediately begin making configuration changes on network devices without a clear understanding of the scope of the problem. This is a regulatory and ethical failure because it risks introducing new issues or worsening existing ones, potentially violating service-level agreements, SLAs, and demonstrating a lack of due diligence. Another incorrect approach is to focus solely on the device that triggered the initial alert, ignoring potential upstream or downstream impacts. This can lead to a missed root cause and prolonged downtime, which is professionally unacceptable and can have financial repercussions for the organization. Ignoring user-reported symptoms and relying solely on automated alerts is also problematic. This can lead to a failure to address the actual business impact, which is a breach of professional responsibility to maintain operational continuity. Professional reasoning. Professionals should approach such situations by first gathering all available data, monitoring alerts, user reports, and recent change logs. Then, they should perform an impact assessment to understand the scope and criticality of the problem. This assessment guides the prioritization of troubleshooting steps. The next phase involves hypothesis generation and testing, starting with the most likely causes based on the impact assessment and system behavior. Documentation of all steps taken and findings is crucial for knowledge sharing and future reference. This systematic process ensures that troubleshooting is efficient, effective, and minimizes risk. Question 8. Regulatory review indicates that while internal network configuration changes are generally within operational discretion, any modification that could potentially impact the availability or performance of customer-facing services requires a documented impact assessment. A network engineer proposes a change to a core routing protocol configuration to improve traffic convergence times. While the change is expected to enhance overall network efficiency, there is a possibility of temporary service degradation or unexpected routing loops during the transition. Which approach best aligns with regulatory expectations and professional best practices for managing this proposed change? Option A. Rely on the vendor's documentation and support to guide the implementation, assuming they have accounted for all potential impacts. Option B. Implement the change during a low-traffic period and monitor network performance closely, assuming the benefits will outweigh any minor temporary disruptions. Option C. Proceed with the change immediately, as the primary goal is to improve network performance, and any issues can be addressed reactively. Option D. Conduct a comprehensive impact assessment that details potential effects on all services, dependencies, and failure scenarios, and develop a detailed rollback plan. The correct answer is D. Conduct a comprehensive impact assessment that details potential effects on all services, dependencies, and failure scenarios, and develop a detailed rollback plan. Explanation. Scenario analysis. This scenario presents a professional challenge due to the potential for widespread service disruption and the need to balance operational efficiency with regulatory compliance. The core difficulty lies in accurately assessing the impact of a proposed network change on critical services, especially when the change is intended to improve performance but carries inherent risks. The pressure to implement improvements quickly can sometimes lead to overlooking thorough impact assessments, which is a common pitfall in network operations. The requirement to adhere to specific regulatory frameworks, even for internal network changes that might indirectly affect service delivery, adds a layer of complexity. Correct approach analysis. The correct approach involves a comprehensive impact assessment that meticulously documents the potential effects of the proposed configuration change on all relevant services and network functions. This includes identifying dependencies, potential failure points, and the severity of any disruption. This approach is best professional practice because it aligns with the principles of responsible network management and proactive risk mitigation. From a regulatory perspective, even if not directly mandated for every internal change, demonstrating due diligence in assessing and mitigating potential impacts is crucial for maintaining service integrity and meeting implicit or explicit service level agreements, SLAs, that may be influenced by regulatory expectations regarding service availability and reliability. This thoroughness helps prevent unintended consequences that could lead to regulatory scrutiny or breaches of service commitments. Incorrect approaches analysis. Implementing the change without a formal impact assessment is a significant regulatory and ethical failure. It demonstrates a disregard for potential service disruptions and a lack of due diligence, which could lead to non-compliance with service availability requirements and damage customer trust. This approach prioritizes speed over safety and reliability. Performing a superficial impact assessment that only considers the immediate network segment is also professionally unacceptable. This failure stems from an incomplete understanding of network interdependencies. It risks overlooking cascading failures in other critical services that rely on the affected segment, leading to broader service outages and potential regulatory noncompliance due to unmanaged service degradation. Relying solely on the vendor's recommendation without independent verification is another failure. While vendor input is valuable, it does not absolve the network administrator of the responsibility to conduct their own thorough assessment. This approach outsources critical decision-making and risk assessment, which is a dereliction of professional duty, and could lead to unforeseen issues not covered by the vendor's scope, potentially resulting in regulatory issues if service levels are impacted. Professional reasoning. Professionals should adopt a systematic approach to network changes. This involves 1. Understanding the proposed change and its intended benefits. 2. Identifying all potentially affected systems, services, and users. 3. Quantifying the potential impact of the change, including the likelihood and severity of disruptions. 4. Developing mitigation and rollback plans. 5. Obtaining necessary approvals based on the impact assessment. 6. Implementing the change during a scheduled maintenance window with close monitoring. 7. Verifying the successful implementation and absence of negative impacts. This structured process ensures that operational improvements are balanced with risk management and regulatory considerations. Question 9. Stakeholder feedback indicates intermittent voice quality degradation on the company's VoIP network, particularly during peak hours. Users report choppy audio and dropped calls. The network engineering team has been unable to consistently replicate the issue in a lab environment. The current network design includes Cisco routers and switches, with CoS policies implemented to prioritize voice traffic. The team is under pressure to resolve this quickly to minimize business disruption. Which of the following approaches best addresses the situation while adhering to professional network management best practices? Option A. Advise users to avoid making calls during peak hours until the issue can be further investigated, and focus troubleshooting efforts on individual user workstations and their local network connectivity. Option B. Temporarily disable certain security features on the network edge, such as deep packet inspection for non-essential traffic, to reduce processing load and observe if voice quality improves. Option C. Implement a temporary, broader CoS policy that prioritizes all real-time traffic aggressively and monitor for improvements, while simultaneously initiating a deep packet inspection analysis on affected network segments to identify specific traffic patterns causing the degradation. Option D. Immediately reboot all core VoIP infrastructure devices, including routers and switches, to clear any potential transient states that might be causing the performance issues, and inform stakeholders that a fix has been applied. The correct answer is C. Implement a temporary, broader CoS policy that prioritizes all real-time traffic aggressively and monitor for improvements, while simultaneously initiating a deep packet inspection analysis on affected network segments to identify specific traffic patterns causing the degradation. Explanation: this scenario presents a common challenge in network troubleshooting, balancing immediate operational needs with long-term stability and security, especially when dealing with a critical service like VoIP. The professional challenge lies in diagnosing a recurring, intermittent issue without causing further disruption or violating established change control and security policies. The pressure to restore service quickly can lead to hasty decisions that might overlook root causes or introduce new vulnerabilities. The correct approach prioritizes a systematic, evidence-based troubleshooting methodology that adheres to established ITIL information technology infrastructure library principles, which are implicitly expected in a CCNP TSHOOT context for maintaining and troubleshooting Cisco IP networks. This involves gathering comprehensive data, analyzing logs, and performing controlled tests to isolate the problem. By following a structured approach, the network engineer ensures that the resolution is not only effective, but also documented, repeatable, and minimizes risk to the production environment. This aligns with best professional practices for network management, emphasizing reliability, security, and compliance with internal policies. An incorrect approach that involves immediately rebooting network devices without proper analysis is professionally unacceptable. This action bypasses the critical step of identifying the root cause, potentially masking the underlying issue and leading to its recurrence. Ethically, it demonstrates a lack of diligence and a failure to uphold the responsibility of maintaining a stable network. From a regulatory or policy perspective, it violates change management procedures, which typically require documented justification and impact assessments before any system modification, especially in a production environment. Such an action could also be seen as a breach of service level agreements, SLAs, if it leads to further downtime or performance degradation without a clear understanding of the problem. Another incorrect approach, such as disabling security features to temporarily improve performance, is also professionally unacceptable and carries significant regulatory and ethical risks. Security is paramount, and compromising it, even temporarily, exposes the network to potential breaches and data loss. This directly contravenes security policies and potentially industry-specific regulations, though none are specified here. The principle remains. It demonstrates a severe lapse in judgment and a failure to prioritize the integrity and confidentiality of the network and its data. A third incorrect approach, focusing solely on user complaints without investigating network infrastructure, is also flawed. While user experience is important, a reactive approach that doesn't delve into the underlying technical causes will likely lead to recurring issues. It fails to address the root problem and can erode stakeholder confidence. Professionally, it indicates a lack of comprehensive troubleshooting skills and an inability to connect user-reported symptoms to network behavior. The professional decision-making process for similar situations should involve 1. Understanding the business impact. Prioritize issues based on their effect on critical business operations. 2. Information gathering. Collect all relevant data including logs, performance metrics, and user reports. 3. Hypothesis generation. Formulate potential causes for the observed behavior. 4. Testing and validation. Design and execute controlled tests to confirm or refute hypotheses. 5. Root cause analysis. Identify the fundamental reason for the problem. 6. Solution implementation. Apply the most effective and least disruptive solution. 7. Verification and documentation. Confirm the resolution and document the entire process. 8. Change management. Adhere to established procedures for implementing changes in a production environment. Question 10. Strategic planning requires a proactive approach to network maintenance and troubleshooting. A critical service outage has been reported, impacting multiple users. The network consists of Cisco routers, switches, and firewalls. The initial report indicates users are unable to access a specific application hosted on a server. What is the most effective and professional initial troubleshooting approach to diagnose and resolve this issue? Option A. Make immediate, Minor adjustments to the core router's routing tables to see if traffic flow can be restored. Option B. Immediately investigate the application server's configuration and logs, as the issue is likely application-specific. Option C. Focus on the firewall rules and security policies, as these are common points of failure for application access. Option D. Begin by verifying physical connectivity and link status on all network devices between the users and the application server. Then progressively check higher OSI layers. The correct answer is D. Begin by verifying physical connectivity and link status on all network devices between the users and the application server, then progressively check higher OSI layers. Explanation: scenario analysis. This scenario presents a common challenge in network troubleshooting, a critical service outage impacting business operations, with multiple potential causes and a tight deadline for resolution. The pressure to restore service quickly can lead to rushed decisions and a deviation from established procedures. The complexity of the network, involving multiple Cisco devices and protocols, further complicates the troubleshooting process. The need to balance immediate restoration with long-term stability and compliance adds another layer of difficulty. Correct approach analysis. The correct approach involves a systematic, layered troubleshooting methodology, starting with the most fundamental aspects of network connectivity and progressively moving up the OSI model. This aligns with best practices for network maintenance and troubleshooting, emphasizing a logical and efficient problem-solving process. By first verifying physical layer connectivity, then data link, and so on, the engineer can isolate the problem to a specific layer or component, minimizing wasted effort and reducing the risk of introducing new issues. This methodical approach is crucial for maintaining network integrity and ensuring compliance with operational guidelines, which often mandate structured troubleshooting to prevent further disruption and facilitate root cause analysis. Incorrect approaches analysis. One incorrect approach involves immediately assuming a complex configuration issue on a core router without verifying basic connectivity. This bypasses fundamental troubleshooting steps, potentially leading to misdiagnosis and wasted time. Ethically and professionally, this is unsound as it prioritizes a speculative solution over a structured, evidence-based approach, increasing the risk of prolonged downtime and impacting business continuity. It also fails to adhere to standard operating procedures that typically require a layered troubleshooting methodology. Another incorrect approach is to focus solely on the application layer, assuming the problem lies with the application itself, without validating the underlying network infrastructure. This is a failure to consider the network as the foundational layer for application services. From a regulatory and ethical standpoint, neglecting the network infrastructure when an application is reported as unavailable is a dereliction of duty, as network engineers are responsible for the health of the network that supports these applications. This approach can lead to significant delays in resolution and damage to the organization's reputation. A third incorrect approach is to make immediate, unverified changes to the network configuration in an attempt to quickly restore service. This is highly risky and unprofessional. It violates the principle of least change and can introduce unintended consequences, exacerbating the problem or causing new outages. Ethically, this demonstrates a lack of due diligence and a disregard for the potential impact on users and business operations. It also hinders effective root cause analysis, making it difficult to identify the true source of the problem. Professional reasoning. Professionals should adopt a structured, layered troubleshooting methodology. This involves 1. Gathering information and understanding the scope of the problem. 2. Formulating hypotheses based on the symptoms. 3. Testing hypotheses systematically, starting with the most basic network layers: physical, data link, network, transport, application. 4. Isolating the fault to a specific component or configuration. 5. Implementing a solution and verifying its effectiveness. 6. Documenting the problem, solution, and lessons learned. This process ensures efficiency, minimizes risk, and promotes continuous improvement in network management. Question 11. Implementation of a proactive network monitoring strategy has revealed intermittent packet loss and increased latency on a critical WAN link connecting 2 branch offices. Users are reporting slow application performance and occasional connection drops. The network infrastructure includes Cisco routers at both ends, with multiple CO-S policies configured to prioritize voice and video traffic. Issue is not constant and appears to occur at random intervals, making it difficult to reproduce during scheduled maintenance windows. What is the most appropriate initial troubleshooting approach to identify the root cause of this intermittent network performance degradation? Option A. Focus troubleshooting efforts exclusively on the application layer, gathering logs from the affected applications and interviewing users to understand the exact nature of their connection drops. Option B. Immediately reconfigure the CoS policies on both WAN routers, increasing the priority for all data traffic to ensure better application performance, and monitor the impact. Option C. Analyze historical performance data from the network monitoring system, focusing on interface statistics, CoS drops, and CPU utilization on the WAN routers during periods of reported degradation. Simultaneously, initiate a series of extended ping and traceroute tests from both branch offices towards each other's internal servers, capturing output for analysis. Option D. Initiate a full network device reload on both WAN routers to clear any potential transient memory issues or stuck processes that might be causing the intermittent problems. The correct answer is C. Analyze historical performance data from the network monitoring system, focusing on interface statistics, CoS drops, and CPU utilization on the WAN routers during periods of reported degradation. Simultaneously, initiate a series of extended ping and traceroute tests from both branch offices towards each other's internal servers, capturing output for analysis. Explanation. This scenario presents a common challenge in network troubleshooting: intermittent performance degradation impacting critical business operations. The professional difficulty lies in isolating the root cause of the problem within a complex, multi-vendor IP network, especially when the issue is not consistently reproducible. The pressure to restore service quickly, coupled with the potential financial and reputational damage of prolonged downtime, necessitates a systematic and evidence-based troubleshooting methodology. Adhering to established best practices and the principles of the TSHOOT exam syllabus is paramount to avoid misdiagnosis and further disruption. The correct approach represents best professional practice because it prioritizes a structured, top-down and bottom-up analysis, leveraging diagnostic tools and methodologies aligned with Cisco's troubleshooting framework. This systematic process ensures that all potential layers of the OSI model are examined, from physical connectivity to application behavior. By gathering baseline data, analyzing logs, and performing targeted tests, the engineer can efficiently narrow down the possibilities and identify the true root cause. This methodical approach minimizes the risk of implementing incorrect fixes, which could exacerbate the problem or introduce new issues, thereby ensuring service restoration and maintaining network stability. This aligns with the professional responsibility to maintain network integrity and provide reliable services. An incorrect approach that involves randomly changing configurations without a clear hypothesis or evidence is professionally unacceptable. This violates the principle of controlled troubleshooting and introduces significant risk. Such actions can lead to unintended consequences, such as disrupting other services or making the original problem harder to diagnose. This demonstrates a lack of analytical rigor and a failure to adhere to professional standards of network maintenance. Furthermore, it could be seen as a breach of professional duty if it leads to further degradation of service without a justifiable basis. Another incorrect approach, such as focusing solely on the application layer without verifying underlying network infrastructure, is also professionally unsound. While the symptoms may appear at the application level, the root cause could be a network issue, e.g., packet loss, high latency, misconfiguration. Ignoring the network infrastructure means missing potential critical failure points, leading to prolonged troubleshooting and an inability to resolve the issue effectively. This demonstrates a failure to apply a comprehensive troubleshooting methodology and could result in a misallocation of resources. Finally, an approach that involves escalating the issue without performing initial, fundamental troubleshooting steps is unprofessional. While escalation is a necessary part of the process when a problem exceeds an individual's expertise or available tools, it should be a last resort after a reasonable effort has been made to diagnose the problem. Premature escalation indicates a lack of initiative and a failure to apply basic troubleshooting skills, potentially delaying resolution and increasing costs. The professional decision-making process for similar situations should involve 1. Clearly defining the problem and its impact. 2. Gathering all available information and symptoms. 3. Developing a troubleshooting hypothesis based on the symptoms and network knowledge. 4. Systematically testing the hypothesis, starting with the most likely causes and progressing through the OSI model. 5. Documenting all steps taken and their results. 6. If the hypothesis is disproven, developing a new one based on the gathered evidence. 7. Escalating when necessary, providing a clear summary of troubleshooting efforts to date. Question 12. Stakeholder feedback indicates that users are experiencing intermittent connectivity issues across multiple departments, coinciding with a spike in unusual network traffic patterns detected by monitoring tools. Initial analysis suggests a potential internal security threat or a misconfiguration impacting a core network segment. The business operations team is pressing for an immediate resolution to minimize downtime. What is the most appropriate course of action for the network operations team to take? Option A. Escalate the issue to senior management and request a temporary shutdown of all non-essential network services until the problem can be fully diagnosed. Option B. Isolate the suspected network segment to prevent further propagation of the issue. Then proceed with detailed log analysis and traffic pattern investigation to identify the root cause before implementing any remediation. Option C. Immediately implement a broad firewall rule change to block all traffic from the suspected source IP addresses to prevent any further malicious activity without further investigation. Option D. Revert the network configuration to the last known stable state across all affected segments to restore connectivity as quickly as possible. The correct answer is B. Isolate the suspected network segment to prevent further propagation of the issue, then proceed with detailed log analysis and traffic pattern investigation to identify the root cause before implementing any remediation. Explanation. This scenario presents a common challenge in network troubleshooting, balancing immediate operational needs with long-term security and compliance. The core difficulty lies in the potential for a quick fix to introduce vulnerabilities or violate established security policies, which could have significant repercussions. The need to restore service rapidly must be weighed against the risk of exacerbating a security incident or creating a new one. The correct approach prioritizes containment and investigation before implementing any changes. This aligns with best practices in incident response and security management. By isolating the affected segment, analyzing logs, and identifying the root cause, the team can ensure that any remediation steps are targeted and do not inadvertently spread the issue or compromise other systems. This methodical approach is crucial for maintaining the integrity of the network and adhering to security policies, which are often implicitly or explicitly tied to regulatory compliance frameworks that mandate secure handling of network incidents. Implementing a broad firewall rule change without a thorough understanding of the attack vector is a significant regulatory and ethical failure. It risks blocking legitimate traffic, disrupting business operations, and potentially failing to address the actual security threat. This could violate service-level agreements and, in regulated industries, could lead to non-compliance with data protection or operational security mandates. Similarly, immediately reverting to a previous configuration without understanding the cause of the current issue is problematic. While seemingly a quick fix, it might reintroduce the vulnerability or fail to address the underlying problem, leaving the network exposed. This demonstrates a lack of due diligence and a failure to follow proper incident response protocols, which are often a requirement for regulatory compliance. Professionals should approach such situations by first activating their incident response plan. This plan should outline steps for containment, eradication, and recovery, emphasizing data gathering and analysis. The decision-making process should involve a risk assessment, considering the potential impact of both taking action and delaying action. Communication with stakeholders, including management and potentially legal or compliance teams, is also vital to ensure transparency and alignment on the chosen course of action. Question 13. The efficiency study reveals a pattern of intermittent packet loss affecting a critical Cisco Catalyst switch in a US-based financial services network, leading to sporadic application slowdowns and potential transaction failures. The network engineer is tasked with resolving this issue promptly to ensure continuous trading operations and compliance with SEC regulations regarding transaction integrity. The engineer has access to various diagnostic tools and the network's current configuration, Which of the following troubleshooting approaches best aligns with professional best practices and regulatory compliance in this scenario? Option A. Isolate the affected switch from the production network by disabling its interfaces and inform users that the issue is being investigated without providing a timeline for resolution. Option B. Immediately reboot the affected switch and all upstream devices to clear any potential transient states, documenting the action as a preventative maintenance measure. Option C. Analyze switch interface statistics, error counters, and traffic patterns using CCNP and net flow data, correlate findings with application performance logs, and consult the Network Change Control Board for any proposed configuration modifications. Option D. Focus solely on the application logs to determine if the application itself is experiencing performance issues, assuming the network infrastructure is functioning optimally. The correct answer is B. Immediately reboot the affected switch and all upstream devices to clear any potential transient states, documenting the action as a preventative maintenance measure. Explanation. The efficiency study reveals a recurring pattern of intermittent connectivity issues affecting critical financial trading applications within a US-based investment firm. This scenario is professionally challenging because network instability directly impacts revenue generation, regulatory compliance, e.g., SEC reporting deadlines, and client trust. The firm operates under strict U.S. financial regulations, including those enforced by the SEC and FINRA, which mandate robust and reliable systems for trading and record-keeping. Any downtime or performance degradation can lead to significant financial penalties, reputational damage, and potential legal repercussions. The pressure to resolve these issues quickly while ensuring no data is compromised or regulatory reporting is missed requires a systematic and compliant troubleshooting approach. The correct approach involves a methodical, data-driven troubleshooting process that prioritizes identifying the root cause of the intermittent connectivity. This includes analyzing network logs, performance metrics, and application-level data, while strictly adhering to the firm's established change management procedures and security policies. This approach is best professional practice because it minimizes the risk of introducing further instability or security vulnerabilities. By following documented procedures and obtaining necessary approvals before implementing changes, the network engineer demonstrates due diligence and compliance with internal controls and external regulatory expectations for system integrity and security. This methodical approach ensures that solutions are not only effective, but also sustainable and auditable. An incorrect approach would be to immediately implement a broad, unapproved network configuration change, such as disabling a firewall rule or increasing buffer sizes across multiple devices, without proper analysis or authorization. This is a regulatory and ethical failure because it bypasses the firm's change management process, which is often a requirement for compliance with regulations like Sarbanes-Oxley, SOX, or specific SEC/FINRA rules regarding system controls and audit trails. Such an action could inadvertently create a security loophole, expose sensitive data, or violate network segmentation policies, leading to significant compliance breaches. Another incorrect approach would be to blame a specific vendor or application team without conducting thorough internal network diagnostics, which is professionally irresponsible and hinders collaborative problem-solving. This can lead to wasted resources, delayed resolution, and a breakdown in interdepartmental trust, all of which are detrimental to maintaining a compliant and efficient operational environment. The professional decision-making process for similar situations should involve 1. Incident triage and prioritization. Immediately assess the impact on critical services and regulatory compliance. 2. Information gathering. Collect all available data from monitoring tools, logs, and user reports. 3. Hypothesis generation. Formulate potential causes based on the gathered data. 4. Controlled testing and verification. Implement diagnostic steps in a controlled manner, ideally in a lab environment or during scheduled maintenance windows to validate hypotheses. 5. Change management. Adhere strictly to the firm's change control process for any proposed solution. 6. Documentation and communication. Thoroughly document all steps taken, findings and resolutions, and communicate progress to stakeholders. 7. Post-incident review. Analyze the incident to identify lessons learned and improve future response capabilities. Question 14. Compliance review shows that a critical business application is experiencing intermittent packet loss, leading to user complaints and degraded performance. The network infrastructure includes Cisco routers and switches. The troubleshooting team needs to identify the root cause efficiently and effectively. Which of the following approaches is the most professional and effective for diagnosing this issue? Option A. Begin by examining the physical layer interfaces of the affected servers and network devices. Then progressively investigate the data link, network, and transport layers, forming and testing hypotheses at each stage. Option B. Immediately reconfigure quality of service, CoS policies on all core network devices to prioritize the application's traffic, assuming bandwidth congestion is the cause. Option C. Focus exclusively on analyzing the application logs for error messages, assuming the network is functioning correctly. Option D. Implement a network-wide configuration rollback to a previous known good state without performing any initial diagnostics. The correct answer is A. Begin by examining the physical layer interfaces of the affected servers and network devices, then progressively investigate the data link, network, and transport layers, forming and testing hypotheses at each stage. Explanation. Scenario analysis. This scenario presents a common challenge in network troubleshooting where a critical application's performance is degraded, impacting business operations. The challenge lies in isolating the root cause of the intermittent packet loss within a complex, multi-vendor IP network. The pressure to restore service quickly is high, but a hasty, unscientific approach can lead to further disruption or misdiagnosis. The requirement to adhere to the TSHOOT v2.0 exam scope means focusing on Cisco iOS-based troubleshooting methodologies and best practices relevant to that environment, without venturing into areas outside the exam's purview. Correct approach analysis. The correct approach involves a systematic, layered troubleshooting methodology, starting with the most likely causes and progressively moving to more complex ones. This aligns with the OSI model or TCP/IP model principles, which are fundamental to network troubleshooting. For this scenario, beginning with physical layer checks interface status, cable integrity, and then moving to data link layer (VLAN), banning tree and network layer (IP addressing), routing (ACL), is the most professional and efficient method. This methodical approach ensures that simpler, more common issues are ruled out first, saving time and resources. It also minimizes the risk of introducing new problems by making changes without understanding the current state. This systematic process is implicitly supported by the Cisco methodologies emphasized in the TSHOOT exam, which prioritize logical progression through the network stack. Incorrect approaches analysis. Making broad configuration changes across multiple devices without a clear hypothesis or baseline data is a significant regulatory and ethical failure. It violates the principle of least privilege and can lead to unintended consequences, potentially causing more widespread network instability. This is professionally unacceptable, as it demonstrates a lack of systematic troubleshooting and a disregard for the potential impact on other services. Focusing solely on application-level logs without verifying network connectivity and performance is also a failure. While application issues can cause perceived network problems, assuming the application is the sole culprit without investigating the underlying network infrastructure is premature. This approach ignores the possibility of network-induced packet loss affecting the application. Implementing a new, unproven CoS policy to prioritize the affected traffic without understanding the current CoS configuration or the nature of the packet loss is another failure. This is a reactive measure that doesn't address the root cause and could inadvertently exacerbate the problem by misallocating bandwidth or dropping legitimate traffic. It demonstrates a lack of understanding of the network's current state and the potential impact of configuration changes. Professional reasoning. Professionals should adopt a structured troubleshooting methodology, often referred to as the top-down or bottom-up approach, or a hybrid. This involves forming a hypothesis, testing it systematically, and isolating the problem to a specific layer or component. Documenting baseline performance metrics before making any changes is crucial. When faced with intermittent issues, the focus should be on identifying patterns, correlating events, and using diagnostic tools like ping, traceroute, debug commands, and packet captures to gather evidence. The TSHOOT exam emphasizes understanding Cisco iOS commands and features for diagnosing and resolving network issues, reinforcing the need for a methodical, evidence-based approach. Question 15. Investigation of intermittent packet loss affecting a critical application hosted on a server in a remote branch office reveals that the issue is not consistently reproducible. The network infrastructure includes Cisco routers and switches, and the server is connected via a Cisco Catalyst switch. What is the most effective initial troubleshooting approach to diagnose the root cause of this intermittent packet loss? Option A. Immediately analyze the application logs on the server and review firewall policies for any potential blocking or rate-limiting configurations. Option B. Initiate a series of high-volume ping tests from the server to multiple destinations across the network to saturate the links and force the issue to manifest. Option C. Verify physical layer connectivity, check interface status and error counters on all relevant Cisco devices in the path, and then examine Layer 2 forwarding tables and Layer 3 routing tables for any anomalies. Option D. Reconfigure the quality of service, QoS, settings on the core Cisco routers to prioritize traffic for the affected application, assuming it is a bandwidth contention issue. The correct answer is C. Verify physical layer connectivity, check interface status and error counters on all relevant Cisco devices in the path, and then examine Layer 2 forwarding tables and Layer 3 routing tables for any anomalies. Explanation. This scenario presents a common challenge in network troubleshooting, identifying the root cause of intermittent connectivity issues in a complex, multi-vendor environment. The professional challenge lies in the need to isolate the problem without causing further disruption to critical services, while adhering to established operational procedures and potentially service-level agreements, SLAs. The intermittent nature of the problem makes it difficult to reproduce and diagnose, requiring a systematic and thorough approach. The correct approach involves a methodical, layered investigation, starting with the most fundamental aspects of network operation and progressively moving up the OSI model. This aligns with best professional practices for network troubleshooting, emphasizing efficiency and accuracy. By first verifying physical layer connectivity and basic link status, a network engineer can quickly rule out common and easily identifiable issues. Subsequently, examining Layer 2 forwarding and Layer 3 routing tables helps to pinpoint problems related to MAC address learning, VLAN configurations, or IP address conflicts and routing path integrity. Finally, investigating application-level issues or specific service configurations addresses the most complex and application-specific problems. This structured methodology minimizes the time spent on irrelevant potential causes and ensures that the most likely culprits are investigated first, leading to a faster resolution and reduced downtime. This approach is also implicitly supported by industry best practices and vendor documentation for troubleshooting, which often advocate for a top-down or bottom-up approach depending on the symptoms. An incorrect approach that immediately jumps to complex configuration changes or application-level diagnostics without verifying the underlying network infrastructure is professionally unsound. This can lead to wasted effort, increased risk of introducing new problems, and a failure to identify the true root cause if it lies at a lower network layer. For instance, attempting to reconfigure routing protocols or firewall rules before confirming that the physical links are up and the devices are reachable would be a significant failure in professional judgment. It bypasses essential diagnostic steps and demonstrates a lack of systematic problem solving. Another incorrect approach might be to solely rely on automated tools without manual verification. While automation is valuable, it can sometimes miss subtle issues or misinterpret data, especially in intermittent scenarios. A professional must be able to critically evaluate the output of automated tools and supplement them with manual investigation. This failure to perform comprehensive, layered diagnostics can lead to prolonged outages and a breach of implicit professional duty to resolve issues efficiently and effectively. The professional decision-making process for such situations should involve 1. Gathering all available information about the symptoms, including when they occur, what services are affected, and any recent changes. 2. Formulating a hypothesis about the potential root cause based on the gathered information. 3. Developing a troubleshooting plan that systematically tests the hypothesis, starting with the simplest and most probable causes. 4. Executing the plan, documenting each step and its outcome. 5. If the hypothesis is disproven, revising the hypothesis and adjusting the plan. 6. Escalating the issue if necessary, providing clear and concise documentation of the troubleshooting steps taken. Question 16. What factors determine the most effective troubleshooting methodology for intermittent packet loss affecting a critical VoIP application in a Cisco IP network? Option A. The most recent configuration changes made to the network devices, regardless of their relevance to the affected application. Option B. The OSI model layer where the symptoms are most evident, the availability of diagnostic tools, and the potential impact of troubleshooting steps on other network services. Option C. The personal experience of the network engineer with similar past issues and the perceived urgency of the end user's complaint. Option D. The complexity of the network topology and the number of vendors involved in the network infrastructure. The correct answer is B. The OSI model layer where the symptoms are most evident, the availability of diagnostic tools, and the potential impact of troubleshooting steps on other network services. Explanation. This scenario presents a common challenge in network troubleshooting, identifying the root cause of intermittent connectivity issues that affect a critical business application. The challenge lies in the elusive nature of the problem, which can be difficult to reproduce and diagnose. Network engineers must employ a systematic and thorough approach to isolate the fault without causing further disruption to services. The regulatory framework for this exam, focusing on Cisco IP networks, implies adherence to industry best practices and Cisco's recommended troubleshooting methodologies. The correct approach involves a methodical process of gathering information, analyzing symptoms, and testing hypotheses. This aligns with professional network engineering standards, which prioritize minimizing downtime and ensuring service availability. By leveraging diagnostic tools and understanding the OSI model, engineers can efficiently pinpoint the source of the problem. This systematic approach is implicitly supported by the need for reliable network infrastructure, which is crucial for business operations and compliance with service-level agreements, SLAs, though specific external regulations are not directly cited for this exam's scope. Incorrect approaches often stem from a lack of systematic methodology, premature conclusions, or the use of disruptive troubleshooting techniques. For instance, randomly changing configurations without understanding the impact could violate the principle of least disruption and potentially lead to further outages, impacting business continuity. Focusing solely on one layer of the OSI model without considering interactions with other layers can lead to misdiagnosis. The absence of proper documentation and change control, often implied in professional environments, can also be considered an ethical lapse as it hinders collaboration and future troubleshooting efforts. Professionals should approach such situations by first understanding the reported symptoms and their impact. This is followed by gathering relevant data from network devices, logs, interface statistics, configuration. Next, they should form hypotheses based on the data and test these hypotheses using non-disruptive methods where possible. If disruptive testing is necessary, it should be planned, communicated, and executed during maintenance windows. The process should be iterative, refining hypotheses as new information becomes available. Question 17. When evaluating intermittent application performance degradation across a Cisco IP network, which troubleshooting approach best aligns with professional best practices for maintaining network stability and operational integrity? Option A. Immediately revert recent configuration changes on the core routing devices, as these are often the source of network instability. Option B. Randomly restart network devices in the suspected path of the application traffic to see if the issue resolves. Option C. Systematically analyze network traffic captures and device logs, correlating performance metrics with configuration changes and known issues before proposing a solution. Option D. Focus solely on the application server's performance metrics and logs, assuming the network is functioning correctly. The correct answer is C. Systematically analyze network traffic captures and device logs, correlating performance metrics with configuration changes and known issues before proposing a solution. Explanation. Scenario analysis. This scenario presents a common challenge in network troubleshooting. A critical application is experiencing intermittent performance degradation, impacting business operations. The challenge lies in isolating the root cause across multiple network layers and potential failure points, while adhering to strict operational procedures and minimizing further disruption. The pressure to restore service quickly can lead to hasty decisions, making a systematic and evidence-based approach paramount. The intermittent nature of the problem further complicates diagnosis, as symptoms may not be consistently present. Correct approach analysis. The correct approach involves a methodical, top-down or bottom-up troubleshooting methodology, prioritizing data collection and analysis. This aligns with best professional practices for network maintenance and troubleshooting, emphasizing the importance of understanding the network's behavior under normal and abnormal conditions. By systematically examining logs, performance metrics, and configuration details at each layer, the technician can build a comprehensive picture of the network's state. This data-driven approach ensures that the identified solution directly addresses the root cause, rather than merely treating symptoms. This is crucial for maintaining network stability and preventing recurrence, which is a core tenet of professional network engineering. The focus on evidence and logical deduction minimizes the risk of introducing new problems or violating established operational guidelines. Incorrect approaches analysis. One incorrect approach involves immediately implementing configuration changes on network devices without sufficient diagnostic data. This is a direct violation of professional best practices, as it risks exacerbating the problem or causing unintended outages. Such actions can be seen as negligent, as they bypass the due diligence required to understand the issue. Another incorrect approach is to solely rely on user reports without independent verification. While user feedback is valuable, it is often subjective and may not accurately reflect the underlying technical issue. Failing to gather objective network data to corroborate or refute user claims demonstrates a lack of thoroughness and can lead to misdiagnosis. A third incorrect approach is to focus on a single network device or protocol in isolation, ignoring potential interdependencies. Networks are complex systems, and a problem in one area can manifest symptoms in another. This narrow focus can lead to wasted time and effort chasing the wrong leads, ultimately delaying resolution and potentially causing further service degradation. Professional reasoning. Professionals should adopt a structured troubleshooting methodology, such as the OSI model or a similar layered approach. This involves defining the problem, gathering information, analyzing symptoms, forming hypotheses, testing hypotheses, and implementing solutions. Critical thinking, logical deduction, and a deep understanding of network protocols and device behavior are essential. Always prioritize data collection and analysis before making any changes. Document all steps taken and findings. When in doubt, consult documentation, colleagues, or vendor support. The goal is to achieve a swift and accurate resolution while minimizing risk and adhering to established operational procedures. Question 18. The performance metrics show intermittent packet loss and increased latency affecting a critical customer-facing application. Network engineers have observed these symptoms across multiple user sessions, but the issue is not constant. The current network infrastructure includes Cisco routers and switches, with the application hosted on servers connected to the network. Which troubleshooting approach is most aligned with professional best practices for resolving this type of intermittent network issue? Option A. Begin by systematically analyzing the physical and data link layers for any anomalies, then progress to the network and transport layers, correlating findings with application-level behavior and utilizing diagnostic tools like ping, traceroute, and packet captures. Option B. Focus solely on reconfiguring the application's network settings, as application-level issues are often the cause of performance degradation. Option C. Immediately assume a hardware failure on the core routers and initiate a hardware replacement process to quickly restore service. Option D. Rely entirely on automated network monitoring tools to identify the problem, making configuration changes based solely on their alerts. The correct answer is A. Begin by systematically analyzing the physical and data link layers for any anomalies, then progress to the network and transport layers, correlating findings with application-level behavior and utilizing diagnostic tools like ping, traceroute, and packet captures. Explanation. The performance metrics show intermittent packet loss and increased latency on a critical customer-facing application hosted on Cisco routers. This scenario is professionally challenging because the intermittent nature of the issue makes it difficult to pinpoint the root cause, and the impact on a customer-facing application necessitates a swift and accurate resolution to maintain service-level agreements, SLAs, and customer trust. The pressure to resolve quickly can lead to hasty decisions. The correct approach involves a systematic, layered troubleshooting methodology, starting with the physical layer and progressing through the data link, network, and transport layers, while correlating findings with application-level behavior. This aligns with best professional practices for network troubleshooting, emphasizing a methodical and evidence-based approach. Specifically, it adheres to the principles of the TSHOOT exam by focusing on the practical application of troubleshooting tools and techniques within a Cisco IP network environment. There are no specific U.S. regulatory frameworks directly dictating network troubleshooting methodologies for private enterprises in this context, but ethical considerations of due diligence and professional responsibility are paramount. An incorrect approach that immediately jumps to reconfiguring the application or assuming a hardware failure without proper verification is professionally unacceptable. This bypasses essential diagnostic steps, potentially leading to misdiagnosis, unnecessary downtime, and wasted resources. Ethically, it demonstrates a lack of due diligence and a failure to apply systematic problem solving, which could violate professional standards of competence and care. Another incorrect approach might be to solely rely on automated tools without human analysis. While automation is valuable, it can miss subtle issues or misinterpret data. A professional must be able to interpret the output of these tools in the context of the network's architecture and the observed symptoms. Failing to do so can lead to overlooking critical clues. A further incorrect approach would be to make configuration changes on production equipment without a clear understanding of the potential impact or a rollback plan. This is a direct violation of professional responsibility and could lead to widespread service disruption, impacting customer satisfaction and potentially violating contractual obligations. The professional decision-making process should involve 1. Clearly defining the problem and its impact. 2. Gathering all available data, performance metrics, logs, user reports. 3. Formulating hypotheses based on the data. 4. Testing hypotheses systematically using appropriate tools and techniques, starting from the lowest OSI layer. 5. Documenting all findings and changes. 6. Escalating or seeking assistance when necessary. This structured approach ensures that troubleshooting is efficient, effective, and minimizes risk. Question 19. Benchmark analysis indicates that a critical customer-facing application is intermittently unavailable, with users reporting slow response times and complete outages. The network team has been alerted and is tasked with diagnosing and resolving the issue. The initial reports suggest a network-related problem, but the exact layer of the OSI model affected is unclear. Which troubleshooting approach best aligns with professional best practices for maintaining network stability and compliance in such a scenario? Option A. Focus exclusively on analyzing application logs and performance metrics, assuming the network infrastructure is functioning correctly. Option B. Begin by verifying physical layer connectivity and basic IP addressing for the affected servers and network devices. Then proceed to examine Layer 3 routing and finally application-level diagnostics. Option C. Immediately restart all network devices in the path between the users and the application servers to clear any potential transient issues. Option D. Prioritize reconfiguring routing protocols and quality of service (QoS) settings to optimize traffic flow before verifying basic network connectivity. Correct answer is B. Begin by verifying physical layer connectivity and basic IP addressing for the affected servers and network devices, then proceed to examine Layer 3 routing and finally application-level diagnostics. Explanation: Scenario analysis. This scenario presents a common challenge in network troubleshooting where a critical service outage impacts business operations. The professional is tasked with restoring service quickly while adhering to established procedures and minimizing further disruption. The pressure to resolve the issue rapidly can lead to rushed decisions, potentially overlooking critical diagnostic steps or security implications. The challenge lies in balancing the urgency of the situation with the need for a systematic and compliant troubleshooting methodology. Correct approach analysis. The correct approach involves a systematic, layered troubleshooting methodology, starting with the most fundamental aspects of the network and progressively moving up the OSI model. This aligns with best professional practices for network maintenance and troubleshooting. Specifically, verifying physical connectivity and basic IP addressing, Layer 1 and Layer 2, before examining routing protocols, Layer 3, and application-level issues is crucial. This methodical approach ensures that simpler, more common problems are ruled out first, preventing unnecessary complexity and wasted effort. It also minimizes the risk of introducing new issues by making changes to more complex configurations before the root cause is identified. This aligns with the principle of least privilege and minimizing impact, which are implicit in maintaining network stability and security, and are foundational to responsible IT operations. Incorrect approaches analysis. One incorrect approach involves immediately reconfiguring routing protocols without verifying basic connectivity. This is a significant regulatory and ethical failure because it bypasses fundamental troubleshooting steps. It risks misdiagnosing the problem, potentially leading to prolonged downtime and impacting business continuity, which can have financial and reputational consequences. Furthermore, making complex configuration changes without a clear understanding of the underlying issue is a breach of professional responsibility, as it can introduce instability and security vulnerabilities. Another incorrect approach is to focus solely on application-level logs without checking network infrastructure. This is professionally unacceptable, as it ignores the possibility that the application issue is a symptom of a deeper network problem. It can lead to a prolonged outage as the true root cause remains undiscovered. Ethically, it represents a failure to perform due diligence in diagnosing the problem comprehensively. A third incorrect approach is to immediately restart network devices without proper diagnosis. While a reboot can sometimes resolve transient issues, doing so without attempting to gather diagnostic information first is a violation of professional troubleshooting standards. It can mask the underlying problem, making future troubleshooting more difficult, and potentially causing data loss or service interruption during the reboot process. This approach demonstrates a lack of methodical problem solving and can be seen as negligent in a professional context. Professional reasoning. Professionals should adopt a structured troubleshooting methodology, often referred to as the top-down or bottom-up approach, or a hybrid. This involves starting with the physical layer and moving up, or vice versa, systematically isolating the problem. Before making any changes, it is essential to gather as much information as possible through logging, monitoring tools, and command line diagnostics. Documenting all steps taken and their outcomes is also critical for accountability and future reference. When in doubt, consulting documentation, colleagues, or vendor support is a sign of professional maturity. The decision-making process should prioritize restoring service with the least amount of risk and disruption, while ensuring that the root cause is identified and addressed to prevent recurrence. Question 20. The audit findings indicate that a critical network segment handling customer financial data has experienced intermittent connectivity issues, coinciding with unusual traffic patterns detected by the security monitoring system. The technician's primary responsibility is to restore full network functionality while ensuring the integrity and confidentiality of customer data. Which of the following actions best addresses this situation in accordance with best practices for network troubleshooting and security incident response? Option A. Promptly reboot all network devices within the affected segment to clear any temporary glitches and restore normal connectivity as quickly as possible. Option B. Delete all log files from the affected network devices to remove any potentially incriminating evidence and prevent future detection of similar issues. Option C. Restore the affected network segment to its last known good configuration without performing any investigation into the unusual traffic patterns. Option D. Immediately isolate the affected network segment to prevent further potential data exfiltration or modification, and then initiate a detailed forensic investigation to determine the root cause and scope of the unusual traffic. The correct answer is D. Immediately isolate the affected network segment to prevent further potential data exfiltration or modification, and then initiate a detailed forensic investigation to determine the root cause and scope of the unusual traffic. Explanation. The audit findings indicate a potential breach of network security policies related to the handling of sensitive customer data. This scenario is professionally challenging because it requires a technician to balance the immediate need for network functionality with the long-term implications of data security and regulatory compliance. The technician must make a judgment call that could impact customer trust, business operations, and legal standing. The correct approach represents best professional practice because it prioritizes data integrity and compliance with established security protocols. By isolating the affected segment and initiating a forensic investigation, the technician adheres to the principle of minimizing further risk and ensuring that any potential data compromise is thoroughly understood and addressed. This aligns with the implicit regulatory framework governing data protection and network security, which mandates a responsible and systematic response to security incidents. An incorrect approach that involves immediately restoring the affected segment without investigation fails to acknowledge the potential for data exfiltration or modification. This could lead to a violation of data privacy regulations, as it might allow compromised data to remain in circulation or be further exposed. Another incorrect approach, such as simply rebooting all network devices, is a brute force method that ignores the root cause and could mask the evidence of a security breach, hindering any subsequent investigation and potentially leading to repeat incidents. A third incorrect approach, which involves deleting logs to clean up the issue, is a direct violation of audit trails and evidence preservation requirements, making it impossible to determine the scope of the incident and potentially constituting obstruction of an investigation. These actions would be professionally unacceptable and could carry significant legal and ethical repercussions. Professionals should employ a structured incident response framework. This involves 1. Identification of the incident, 2. Containment of the incident to prevent further damage, 3. Eradication of the threat, 4. Recovery of affected systems, 5. Lessons learned to prevent future occurrences. In this scenario, the immediate priority is containment and investigation, followed by recovery.